Good afternoon, everyone. I'm Erno, and I'm representing both Informator and Cydrill, as you may know us already. So this webinar this afternoon will be about integer problems in code, and basically before we deep dive into what can possibly go wrong with integers in your code. I will have, so a little bit about the agenda. So what you can expect for the next hour or so. The presentation will go for some maybe 50 minutes, 45, 50 minutes, and then we will have a Q&A part after that. And the topic, as I said, will be about integer overflows. At the beginning, before I deep dive, as I said, into the topic, we'll have a short introduction to what software security is all about, what makes it a special topic, why it is not simply IT security, what you have to keep in mind regarding all this, and then we'll start talking about integers. So let's do this because the time is never enough. Actually, when we do teaching, we know all the time that we have much more topics than that would be absolutely necessary. So as I promised you, we'll start with a little bit of intro to what security is all about in this context. So application security, as I said, is not cybersecurity as such. It's not IT security even. It's it's part of all this, but you have to see clearly how it is positioned within this universe of cybersecurity. Of course, when we talk about cybersecurity in the context of software, it's all about actually bugs. At the end of the day, when developers make mistakes in their code, those mistakes introduce may introduce certain security problems in their code, and that weakness as a consequence of a bug in the code actually implies the possibility for the bad guys to break into your applications, to steal personal data, to steal system data from the application, and so on and so on. So when we talk about software security in the context of cybersecurity, we always have to talk about bugs. Mainly, this is what we teach to developers. So we usually say that we teach developers how not to code because they already know how to code. We teach them how not to, because it is all about those mistakes that they commit. Given the fact that cybersecurity or software security is about bugs, if we put that together with another very important fact, which is that basically there is no software without a bug. If you know Murphy's law of coding, the simplified version or the simple version says that there is, so each and every non-trivial program has at least one variable, at least one loop, at least one branch, and at least one bug, right? And I pretty much like the extended version of the Murphy's law of coding, which says that each software has exactly 5 bugs, and this number does not depend on the number of the bugs that have been found already. Yeah, this is an unfortunate situation for those developing software. They know this pretty well. But if you put this together, like software security is about bugs, secure coding is about bugs, and there is no software without a bug, you easily come to a very painful, actually apocalyptic even conclusion, which means that there is no such thing as 100% secure software. Nobody can actually reach an unbreakable and unhackable software. So this is the starting point of the whole journey, no matter if you're talking about managers managing software development projects, or developers developing code, or architects, or even testers trying to find all these bugs in the code. The journey starts with this pretty harsh statement: there is no such thing as 100% security. I also have some good news, because this is pretty bad news. So you may even say, okay, so this guy just said there is no chance to win this war. And indeed, we cannot eradicate completely hacking, and we cannot make our software 100% secure, simply because there always be some bugs, there always be some mistakes. Developers are human beings, and we human beings, we make mistakes. Even developers, right? But good news. So the good news is that while there is no such thing as 100% security, we can actually achieve 90%. Where does this number come from? So how come? Actually, there are several studies done by Microsoft, by antivirus companies, by Gartner, and all they surprisingly came up with more or less the same number. So this number 90. So number 90 is kind of an objective data, seems to be pretty much inherent feature of the world in which we live in. What's this 90%? So all these companies and all these surveys revealed that actually 90% of those incidents that happened in the wild, they originated from some very well-known problems. So no matter how you approach it, you realize that basically once you start following the best practices and you once start doing secure coding and learn all about everything about all those best practices that you have to follow when coding, you have the chance, theoretically, of course, to get rid of 90% of the incidents. Now, this is something worthwhile doing, right? So while we cannot ever achieve 100%, we do have a good chance to achieve 90%, and that is why developers should be aware of these best practices so that they can start coding in a secure way, thinking about all those problems, all those mistakes, and how to avoid them. This is what we teach, of course, in our courses. The other question usually when we discuss with managers and they say, okay, they understand, okay, so 90% can be achieved, we can get rid of 90%, there is no way we can get rid of 100% and all of the security problems, but how much will it cost? So what should we do and how much it will cost us? What about the resources? What about the headcount? Should we hire somebody? Should we hire a security expert? Should we put a security expert in each and every development group, or should we allocate 2 weeks extra on top of each and every development project? Here I have good news. Actually, in most cases and from most of the aspects, doing secure coding, basically following those best practices, is free, kind of free, of course. I mean, no, nothing is free, of course, but it does not really need extra resources. It's simply about the mindset of the developer. So if in a course, if the developer learns about the best practices, about coding related to security and how to avoid security problems, changing the developer's mindset towards these things is the burden of the job you have to do to achieve a secure product, a secure software product at the end of the day. It's not an extra time. It's not an extra headcount. It's simply doing it differently. It's not doing more. It's doing the same amount of work, but in a different way. So this is pretty convenient thing. Of course, the only investment you need to do is to sit into a secure coding class, or of course, read secure coding sources of information on the internet, learn about these best practices, and change the way how you write your code. But it's nothing extra. So this changing how you write your code as a developer is basically what paranoia is all about. So basically, doing secure coding on a very, very high level is basically being paranoid about your code, not forgetting about the fact that there are bad guys out there who basically are looking at each and every step of yours, and if you make a mistake, they will jump out from the dark and will strike. Of course, whether they will strike or not does not really depend on like if your code is secure or not, because as I said, it cannot be completely secure. It simply depends on how good your reputation is, because if they know that you are doing the right thing, they will just go and hack somebody else, because they know most probably those things, those sources can be hacked, or those products can be hacked in a much more easier way. And basically, also, if you are developing some juicy target which is worthwhile hacking, they will go for it. So these are the components of if you will be hacked or not. And basically, these are the numbers behind secure coding. One thing I didn't mention, of course, at the end of the day, in real life, you will have to take into account many other things related to like your efforts towards secure coding. So according to Nyer, who is let's say a celebrity in this domain. So he's also a cryptographer. He writes blogs. He talks at conferences. So he's a very well-known guy, and he said once that the goal here is not even 100% security, which we cannot ever achieve, but rather adequate security and at a reasonable cost. So adequate security means, of course, there is a level of security you can reach and nothing beyond that. And even if you invest into like more security there and you do more and you learn more, after a while, you will not get more security while you will keep investing into it. And also reasonable costs. So still you need to know like what costs, what amount of money and how it all comes together. So looking at the whole story, and this is really the summary of my my introduction about software security and secure coding. Looking at the whole story from software from game theory point of view, it's very interesting because you can easily realize, even from what I just explained, you can easily realize that secure coding and software security is an infinite game. Security in general is, by the way, as well. So this is not a zero-sum game. It's not like we lose and the bad guys win, or they win and we lose. So this is not a zero-sum game, but this is an infinite game. And as it is usually in infinite games, the goal is not to beat the enemy. The goal is simply to stay in the game. What do I mean by this? You as a company or you as an individual, your goal is to stay on the market. Your goal is to do the right thing, not to be kicked out from the game, which is basically the market in this case. And that means you have to deal with security for a single reason, so that people keep buying your products. Because the most important loss that you can have in this domain, of course, there is GDPR. Of course, I mean, related to this, you can have many different costs and many different damages that you may have. But the most important loss that you can ever have in this domain is the loss of reputation. So if the market realizes that you are doing the right thing from quality, generally from quality point of view, but also from the point of view of security as part of a quality indicator of your software, the market will keep buying your product. Customers will keep buying your product. If you lose reputation, they will stop buying your product and you will get out of the game. So this is the story. This is what you have to keep in mind related to all this. And as I promised you, this is the introduction, after which we will now start discussing finally the integer problems. As you can guess, this is a really small subpart of all the possible problems related to your code written no matter in which programming language. Somehow basically this day we will have C and C++ in the focus, but basically the thing I'm talking about here, or will talk about here, are pretty much generic problems present in Java, in C# and in many other programming languages that deal with native integers when you deal with numbers in your code. And this is perfectly true for most of the topics that we teach and most of the secure coding issues that we discuss. No matter what, like object-oriented programming, then of course it's more C++ than C, but this is also a very common problem in Java and C#. I mean, we are talking about very more common problems in C# and Java. Input validation in general, it doesn't really matter what programming language you're using. How you do authentication, how you do authorization, how you apply cryptographic operations. Of course, the APIs are different. Of course, the syntax may be different, and this is a different programming language, but the problems are pretty common. Many of the problems, let's put it in this way, are pretty common across all programming languages. And actually, integer problems are no different. The story is perfectly true for integer problems as well. So in all those programming languages, you have very similar problems. So the first question and the first very interesting issue related to integer problems is, I know it's a kind of stupid word or a strange word, but it's basically the mental representation of integers in your head. So when you close your eyes and somebody tells you, okay, imagine integers, I mean, all of integers, all of them, draw on the board, like how you imagine integers, how they look like in your head. Most probably you will come up with an axis, like as you can see that on the slide. If it is a signed integer, we put a 0 in the middle, saying, okay, this is 0, and then we have positive and negative values all the way. All the way to what? And that's also a good question always, because in real life mathematics, I call it real life, or we can also call it human mathematics. When we talk about numbers, they're infinite. So we have 0 in the middle, and we have a positive and the negative infinity, and we have all the numbers on this axis on the two sides of the 0. However, we all know, and this is why I usually say that integer problems are the unknown knowns. You know, this known unknown, unknown unknown, and known unknown thing from software security, and also from the Johari window, if you ever studied that one. Whatever, but there is a missing fourth element, which is the unknown known. We all know how integers work, but we usually don't think about these things when we write our code. So to go back to the slide, we draw axis, and then we put 0, and we have all the numbers. But we all know that there is a limit. We all know that we are on a 32-bit arithmetic or a 64-bit arithmetic, no matter what. And then we all know that basically we have to put a limit there. So you have the minimum and you have the maximum value for the integer that you represent in your computers. And this is not true. This is not like this. This is not the same story in case of in case of real life mathematics, because there the numbers are infinite. In the computer, they are not. Also, similarly, in the computer, we have the signed and the unsigned types, as you may know. And this is why the other way of drawing this axis is to put a 0 here and to go to max. But then the next question is, okay, numbers are limited in computers, so we don't have infinite values that we can represent, because depending on our architecture, it is 32-bit, 64-bit, even maybe 16-bit, or if you already lived in the 80s, then it was even 8 bits, whatever. So we know there is a limit, but then the question is, what if we do an arithmetic operation, like we add two numbers together, and the result does not fit into the representation that we have. So we have two numbers, we add them together, and the result is bigger than what we can represent in that arithmetics. What happens there? And of course, this is, as I said, yet another unknown known, because we all know what happens. I mean, if I would ask you this, like how this works in computers, you will just say, okay, it's trivial, it's a wraparound. Yes, it is. But given that our mental representation is an axis for all the numbers that we represent, we, in most cases, as we write our code, we simply forget about this fact. And this is at the core of the whole problem. So we all know what happens, but basically we don't write usually our code with that in mind. So this is my first suggestion here. And this is something we also like suggest when we have the real life, I mean, teaching and classes, to persuade developers to imagine numbers, integers on the ring. Don't think about an axis when you have to imagine and you have to think about numbers, but just switch your mind into the ring. So instead of having something like this, just band this together, like take the two ends and just band the axis, and basically have a ring instead in your mind. Why this does help? Because on the ring, it is pretty much obvious that the wraparound will happen and how it will happen, and that will make you, at least to say, harder to forget about the fact that you need to take this into account. You start off from 0, let's say, and as you start incrementing this value, you don't go this way on the axis, but you go this way down here on the ring, and when you reach the maximum value and you add 1 to that, and I mean maximum value is the maximum value for that specific arithmetic architecture that you may have, in most cases 32 bits, maybe 64, then you simply will get the minimum value. So this is what I called the wraparound before, and this is what we, especially with C++ developers, know it perfectly, that this is the case. With a twist I will have in the next slide, and also with some surprises we will have on the next the slide after the next slide. So it is pretty much obvious that you cross this red line, and this red line, this is the bridge where your human thinking about numbers and the numbers as they are represented and handled in computers differ. Actually, when you in real life mathematics add 1 to max, you will have a max plus 1, which is a positive number. But here in the computer, all of a sudden you add 2 positive numbers together, and all of a sudden the result is negative, which doesn't make any sense in real life mathematics, but it completely makes sense on the ring, because this is how the ring works. Actually, if you ever learned linear algebra, we do define the rings there, but that's another story. This is development and not mathematics, and not abstract mathematics even furthermore. And the same stands for unsigned integers. So you start off from 0, you go around, and you arrive to max. And again, here you also have a critical section where the values will differ from real life mathematics, but it's up here left from the 0, of course, because as we go around, we reach the uint max, right? So the maximum unsigned representable value. And if we add that 1 to that, we just arrive back to 0. And it's perfectly valid, as I said, on the ring. And the problem is, as I said, just to repeat once again and to emphasize once again, that this is something we all know, but this is something we don't usually take into account when we write our code, and that paves the way for lots of trouble. So first of all, as we just discussed, if you do an arithmetic operation that results in a value which does not fit, then in C++, in the C and C++, actually is defined as undefined. So you know we have this undefined behavior, and basically the wraparound is not guaranteed by the language. So actually the language defines this situation as undefined behavior, meaning that you should not count on any value here. It can be anything. In reality, let's say in 105% of the cases, and it's literally all of the compilers and all of the architectures, you know, and all of the arithmetic operation implementations will basically do a wraparound, but you have to know that formally it's an undefined behavior. So most compilers will result in a wraparound, as I have just explained that previously on the ring, like this. You will just cross the red line, you will just cross this bridge. But then the next level of problems is that this crossing of the bridge, this crossing of the critical section, where there is a difference between real life mathematics and computer mathematics, happens completely silently. Nobody will let you know. There is no exception in C++. There is not a flag that you can read out in C, which is actually interesting if you think about it. It's not that much interesting in, I mean, it's not that much surprising in, let's say, Java or C#, or Python. Okay, Python is a different thing. In Java and C#, where basically the programming language runs in an interpreter, or you have some kind of language runtime. But the C programming language is basically completely directly compiled into machine code instructions. And as we may already know, the machine code instructions and the processor actually does have a nice flag about this wraparound, the overflow flag, also the carry flag in certain ways. But even though the C++ code is pretty much down to this, basically runs on the CPU directly, even then there is no way you can know about the fact that you just did it, that you just crossed the red line. And this is the problem. No exception, no flags you can read out. And this is why we may even say that it is literally impossible to write correct code without any extra things that we do, because the wraparound can just happen. It will just happen silently, and all of a sudden, some of your assumptions about the values that you handle in your code will be broken. And broken assumption is the hotbed of all kinds of security problems. So they say that each and every successful attack is basically a broken assumption of the developer. So what's this broken assumption? So for example, I have two positive numbers, I multiply them, and obviously in real life mathematics, the assumption is, which stands there, which is a true assumption, is that when you multiply two positive numbers together, the result is positive, right? This is how mathematics work, but not in computer. In computer, actually, when you multiply two positive numbers together, all of a sudden you may end up in a negative value, which doesn't make any sense in real life mathematics, but does make sense. And this is how the ring works. And this is a broken assumption. Is you had such an assumption writing your code, not dealing with negative numbers. All of a sudden, the attacker will feed in some large values if they can, breaking your assumption, triggering the overflow, triggering the wraparound, and basically breaking your assumption in your code. And later on, somewhere your code will be broken, something will go wrong in your code because of handling the necessity of handling negative numbers for which your code was not prepared for. So, of course, in many programming languages, you have to put an explicit casting. In C, C++, depending, of course, you may have certain compiler warnings and everything, but an implicit cast will occur, and you basically will have an unwanted value in your code. So instead of -1, possibly having large numbers. It all depends on whether you are handling signs or unsigns. So, or when you assign a long integer to a short one, we have truncation. So we can have wraparound, we can have truncation, and we can have also implicit casting. So these are all the problems as kind of consequences of this silent wraparound and silent operation of all these things that happen on the ring, which are not aligned to what happens in your mind as a developer, right? So why we are talking about all this in security? So what does this has to do with security? Obviously, they have to do with security, obviously. One of the most dangerous things is when you have an input validation line, which starts to prevent certain dirty inputs to reach your code. And in the typical case, when in the input validation, we have to work with numbers, we do some kind of arithmetic check, whether, let's say, A plus B is smaller than C, because if A plus B is smaller than C, we do some buffer operation. Otherwise, the buffer operation we have to stop because it will overflow the buffer. If the buffer can overflow, that basically is the disaster, which can lead to arbitrary code execution. So that's the worst thing that can happen. We try to stop that with an input validation, but input validation in this case is basically working with integers. If we make a mistake in here, and the attacker can feed in certain buffer sizes and certain values with which the attacker will fool your input validation line, the attacker will be able to slip through the input validation and trigger the unwanted code execution by buffer overflow, for example, which you try to prevent with an input validation. So this is the worst thing that can happen. But in general, yeah, so it can it can lead to a successful buffer overflow despite all the protections that you build into your system. Similar problem can arise from array over-indexing or under-indexing, which all cause instability problems in your code. And whenever instability is there, security problem is there. This is just the generalization of the idea that I gave you before, like how integer overflow can lead to basically arbitrary code execution. There are various real life examples. If you ever played any of these games, you may know this. They also say, I haven't seen that myself, but they also say that for a couple of minutes, maybe hours, even on YouTube, we had a negative value for the as a counter of how many people have seen a certain video. If I remember well, that was the Gangnam Style video, which was the first video that exceeded the 32-bit. I think it was an unsigned 32-bit, maybe it was a signed 32-bit, so it should be something like 2 billion and something views, and all of a sudden it wrapped around simply, and then YouTube developers had to fix this pretty much quickly. But we have much more serious consequences, and believe me, this Swedish stock exchange is not for you here. This is generally one of the examples we bring in. It happens actually, as there's the Stockholm Stock Exchange that had a very interesting problem some 7 or 8 years ago, when somebody by mistake entered a negative number into one of the fields, and that negative number was converted into an unsigned by the system somehow in the Stockholm Stock Exchange system, or some system being used there. And all of a sudden a transaction happened of some $70 billion, which is even more in Swedish crowns, whatever. So it was pretty much comparable to the Swedish GDP, annual GDP basically. And they had to stop the trading for that day and clean up the database before they can restart the trading next day. But also the Ariane rocket. So there are many interesting examples, and we will even have a case study right away. So just to cut it really short, what is the problem here? Again, we spend much more time on this in the class, but let me just explain you quite quickly what this is all about, and I promise you some surprises at the end, for which you most probably will say, how I didn't think about this ever before, because it is so obvious, but I didn't know this is it works like this. So what's this piece of code? So this code exhibit is like a couple of lines of source code. This is a part of a simple command line application that receives two parameters. arg0 is the string length, whatever it is, and args1 is basically the this may be the name of the application, no matter what. It's just a string. And the second command line, so args1, so the second element of the args array, is basically nothing else than a number. So we receive a number there. We turn that number into an integer. Of course, it's all string. And we calculate the length of the first string, and then we print out arg0 concatenated, so the string concatenated with as many x characters as the second parameter is, or the first element in the args array is. But we thought like, okay, but we want to prevent this printout to be too long, so we are checking whether len1 plus len2 is smaller than some kind of max length. Let's say it's 100 or maybe 1000, whatever it is. And then we want to prevent we want to prevent too long string to be printed out. But obviously from now on, I think that whenever you will see an arithmetic operation in your code, you will think about, okay, but can that overflow? And of course, it can. So here we have a situation, unfortunate situation, when if length2, which is obviously provided by the user, which means basically provided by the by the attacker, if len2 is set by the bad guy. Of course, this is just a stupid and very simple command line application. If that value is set by somebody to a large number, for example, to int max, which is what the max int, which is 2 billion, blah, 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 whatever, then we stop the show here. We try to stop the show here, but we don't, because basically, if you take this number, 2 billion and something, which is max int, and you add any positive number, which is the length of the string there, the wraparound will happen. You will get a negative number, and actually negative number as a result of this arithmetic operation is obviously smaller than max length. Of course, unless max length is explicitly indicated to be an unsigned, because then this will be promoted. So the story is of course much more complicated than this, but let's say that max length is an integer. We add len1 plus len2, it will wrap around, it will be a negative number. So we basically will print out the string, which contains a huge amount, which will contain a huge amount of x's, basically 2 billion and something. And this is exactly what we wanted to prevent, right? So this is the problem, pretty much trivial, and so far so good. But then let's say that we explained this to the developer, and the developer said, you are right. Okay, okie dokie, I understand everything. So how about we simplify this check to get rid of the arithmetic operation, actually? So the arithmetic operation is the problematic one because it can lead to a negative number. So how about we just check whether len2 is above or below the limit? not a bad idea. I mean, at least we got rid of the problem. But as you will see, we have another problem here. So the next obvious challenge with it, if you're talking to this developer, the next obvious challenge would be something like, okay, but what if line 2 is a negative number? So, and then the developer would say, so this is now a kind of conversation between a security, a security expert and the developer, like, okay, first you have an overflow there. And then the developer says, okay, but let's get rid of the arithmetic operation, the plus. And then the next challenge from the security expert is, okay, but what if it's a negative number? And then the developer said, no problem, you didn't fool me because I'm using here the ups function, right? So basically, even if this is a negative value, it will be turned to a positive line 2, so no problems, right? And now the surprising thing, and I think, unless of course you have heard about this already, in most cases, not too many of the developers know about this trick or problem. But let me ask you a very simple question. And the question is super simple. What is the absolute value of uint, or max uint? Sorry, what? No, let me formulate the question once again. That was not the right question. What is the absolute value of minint? That is the correct question. So what if the attacker, so the malicious user, sets args1, this one here, to exactly minint, which is minus 2 billion 147 million blah 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 648. I specifically named the last 3 digits 648 because you see an interesting discrepancy, which was already here actually. Let me just go back, because the minimum there is a asymmetry bit on the ring, because as you may know, it's not really nicely visible here. It is actually, it is, because the minimum is exactly below the 0, and we have not much, but one single value less on the right side on the ring than we have on the left side on the ring, as this is exactly visible here on the slide, because you see that the max int is 2 billion blah 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 647, while minint is minus 2 billion blah 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 648. So the surprising question, and I mean, you can answer this question quite easily. You can even deduce the right answer. For the question, let me repeat the question. What is the absolute value of this number? And obviously, if you take a look at this number and then you take a look at the max int, you see that basically we cannot represent the absolute value of minint because there is no such number on our ring. In real mathematics, it would be plus 2 billion 147 million blah 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 648, but we don't have that number. So the absolute value function in this situation is in trouble. What would be the right value to return? Because there is no such value we are looking for, but it has to return something. I don't know if you know by heart the fingerprint of the apps function. It takes an integer and it also returns an integer. So the point is, and this is my surprise, I promise you, as one of the nasty consequences of all this story, like overflowing integers, the ring, the fact that it happens silently, and the fact that we write our code in most cases without this having in our mind. So the surprising thing is that the absolute value function returns positive values. I mean, it's pretty much logical, right? So it always should return absolute value, positive values, as it is an absolute value function, isn't it? Except for this one specific value. If you call absolute value function with minint, it will return minint itself, moreover, a negative value. So if you write your code assuming that the output of an absolute value function is always positive, I have some bad news for you. It's not. In this specific case, for this one single specific value, which is minint, it will return a negative value. It will return minint itself. So if you see this animation here, This is more or less what is absolute value function. So it turns the values from the left side of the ring to the right side of the ring. But this min here, down here, dance is alone. It does not have a pair on the positive side. And as I said, absolute value function here is in trouble, and it will just return you a negative value, and you will actually have to prepare your code to this. You have to either check on the input of apps whenever you call the apps function if the input is exactly min-int, because if it is, it will not work as intended or as you thought, or you have to check the absolute value function's output to check whether it's a negative value. Pretty weird and pretty inconvenient, but this is exactly an example of all those tricks and all those dirty tricks that you have to take into account to write correct code. And because of the fact that we have millions of such problems all around, I may even dare to state this is practically impossible to write correct code that deals correctly with all these integers without doing some extra things. And now, yeah, sorry, let me demonstrate this to you just quickly, and also to give you some insights into like our our environment, our learning environment in which we teach. Let me just restore. Yeah, okay. So what you see here is Visual Studio Code with some C++ code here. I mean, the choice of IDEs, like whatever. And on the right side, no matter which IDE we choose, being Visual Studio Code, for Java we use, for example, IntelliJ IDEA, we have the Cydrill Sergeant. So Cydrill Sergeant is a plugin that we developed, which is basically which gives the context of the environment, sorry, the environment and the context of our teaching. Basically, that's a chatbot that gives you instructions about what you need to do in the lab. As you can see here, we have a very, very simple source code which deals with some integers. And when you start the lab, you start this chatbot and it will keep dropping you instructions about the next step you have to do. Now it says, please build and run the application by using the integer overflow. I already prepared this so that we don't have to deal with all the settings. Integer overflow, let's start it. It will run this in a terminal. And it's a very simple application. It prompts me for a number. Let me just put some random number here. And it prints out the number +1, number -1, casting of the number. It does all kinds of arithmetic operations on the number, both in signed and in unsigned arithmetics. So if I enter 134, these are the values that are printed out. So far, nothing really surprising. Now, if I enter, however, max, so that we don't have to know by heart, what is the max int or the int max. So if we put max, which will basically be max int, this is the value, so 2 billion and something. And what is surprising, I mean, it's not that much surprising, as I said, but it's where we cross the red line is when we print out x plus 1. X plus 1 is actually a negative number. So this is surprising. This is not, in real life mathematics, this is not correct, but on the ring, this is perfectly okay. And also when you take the max, uint max, then of course well, let's say surprising thing is that when we cast it to signed, we got -1. There is also something which you can read out from these two values. Basically, that both 4 billion and something, which is uint max, and -1 are represented in the computer in the same way. So it is, from certain point of view, it's simply like question of how you look at the same number in the computer. So the same hexadecimal FFFFF or all 1 bits. If you look at it from signed perspective, it's -1. If you look at it from the unsigned perspective, it is 4 billion and something. Of course, it does matter. It's not just question of how you look at it. It does matter when you have to compare this value to, let's say, 0, because one is smaller than 0, the other one is bigger than 0. So it does really matter if it is a signed or an unsigned value. Okay, and then let us see last thing, that this is a super, so all of our labs are much more complicated than this. And also we have a fixing lab when we will fix this, triggering exception, for example, when we cross the red line, but this is not something we'll do now. So let me just enter min for the end. And as you can see, when I enter min, it draws my attention to this one. If you didn't believe me up to this point, you can now see in black and white that the absolute value of this specific value, the int min, is itself. And this is something you have to take into account when you write your code. I would say in most of the cases when you write apps in your code, you just assume that the output is positive. Unfortunately, it's not. Okay, so this lab is finished. So this is a quick demonstration. Let me just go through a very quickly. Let me just go through the through a very nice case study. This is something we usually do in our classes, that when we discuss things, we bring in something from the real life. And I suppose to give people some kind of feeling, you know, this is something that that can happen to you as well, because it happened to, in this specific case, it happened to Microsoft, right? The whole story is pretty much interesting because the bug we are talking about that led to WannaCry, because this is the WannaCry story, this bug has been committed by Microsoft yet in 1992. So it was a bug, it was a mistake in a code which was written back in 1992, which is still present in Windows, even in Windows 10 these days. So it was a disaster. It happened in 2017. Some 300,000 computers have been infected. It was a ransomware. It encrypted the disk, and you had to pay some amount of money. Of course, if you pay the amount of money to the bad guys, nothing happened. So they just tried to collect money. The key vulnerability that led to WannaCry was a simple truncation bug. It had to do with integers. It is pretty much connected to the problem we had. And actually in this slide, you see the function which actually turns certain, and the bug was in the server message block protocol, the SMB protocol version 1, and that is the code that has been written yet back in 1992, because in today's Windows 10, and 11, we already have version 3 of this SMB protocol, but for backward compatibility reason, they kept the first version of this SMB protocol active in Windows, and that was the problem. Legacy code is always problematic, and this was a bug that waited for 25 years until somebody figured it out and started to abuse it actively. Of course, by the time the bug has been, WannaCry was written and WannaCry outbreak was happening, Microsoft already provided a patch for Windows 10, but for example, not for Windows XP. So this is what left many of those computers still vulnerable. So to concentrate on the problem, what is the problem here? Of course, this is disassembly of the SMB code, so it's not most probably how the source code looked like, but you see here a pretty nasty thing. Basically, the size of list in bytes, even though it was a 32-bit value, actually the whole arithmetic happened in 16 bits, so in 2-byte arithmetics, basically leaving the upper 2 bytes of the size of list in bytes intact. That means that if you provide a package into which you put 2 bytes on the upper 2 bytes of this double word, so basically 32-bit value, it will be left as is. So you could put there anything. Of course, the lower 2 bytes, the lower 16 bytes, could have been will be overwritten by the function, but not those 2 bytes, the upper 2 bytes of this size of list in bytes, which is, just to repeat, a 32-bit value and not a 16-bit value. So this, even though they meant to override the whole value with the length of the buffer, they just overrode the 2 bytes, and the upper 2 bytes were left intact, so the attacker could craft their package, setting those upper 2 bytes to something, and that caused a buffer overflow, because as you can see, this is basically indicating the size of some things, and those things can overflow with this trick. And due to this overflow, due to the fact that this happens in 16 bits, they were able to trigger a buffer overflow. A buffer overflow was able to trigger arbitrary code execution, and that is how this virus was actually able to spread. So without going into more details, of course, we go into some more details in the class, but basically this single line of source code is the bug, or let's say one of the bugs behind the WannaCry virus not updating, but just this lower half of this word, of this 32-bit value, leaving the possibility for a buffer overflow, remote code execution, and therefore spreading a virus. And as you may remember, or you may know, many of the typically embedded devices or ATMs or some kind of billboards that may have been running still Windows XP were affected and were infected by WannaCry. So what is the lessons learned? Again, just rushing through because the time is already up. Input validation is important, but of course, if we make mistakes there, the consequences can be devastating. WannaCry is a good example for there because it was just an integer mishandling that, you know, it's like a domino. So you have one single mistake that leads to all the rest of the mistakes, or all the rest. So all the dominoes will fall down and the whole system is hacked in that case. Legacy code, it's always problematic. So if you have an old code written like 10, 20 years ago, developers back then maybe were not aware of many of the security problems that we are aware already today. Do hardening. So as I said, it was SMBV1, and of course, nobody uses SMBV1 except for some old peripherals, like very old printers. So it's always a good idea to shut down things from your computer that you don't use. And this is basically what we call hardening or debloating as part of the configuration and configuration management of the devices or the application in which your code runs. And of course, be aware always of the life cycle of the used product. So in this case, Windows XP's life cycle was already over. That's why Microsoft didn't provide any patches for this problem, because the problem was known already by the time WannaCry broke out. But many of the, as I said, many of the Windows operating systems, Windows XPs or even Windows 7s, were not updated because simply there were no patch. Windows 10 was more or less okay, unless you switched off automatic updates for some reason. So specifically for the best practices related to integers, what you can do, you can upcast. Be careful with this. So if you work with 32-bit numbers, it is maybe a good idea to go to 64 bits, do the arithmetics there, but then upcast back then. Because if you just stay in 64 bits from that point of view, it doesn't help, because it's simply that you don't have such a ring, but you have a huge ring then, but still there is a ring, still there is a critical section on that ring. So it's just a bigger ring, but it makes sense if you go up and down all the time. So you work all the way with 32 bits, but when you want to do some kind of arithmetic, you go up, do the arithmetic, and then go back down, or just check whether you can go down back, of course, if you have anything on the upper 32-bit half of the 64-bit value. You can anytime use big num libraries. The good thing about them is that they never run out of bits, so they are dynamic structures and they expand and expand and expand. So of course you can run out of your heap sooner or later if the attacker keeps expanding your numbers, driving your code to larger and larger and larger numbers. Of course, these big num libraries are not have not been created for this specific reason. They are created for typically for cryptographic operations needed by RSA or some other cryptographic libraries or algorithms, but they come in handy here as well because there is no overflow in them. Of course, I didn't talk about efficiency of these libraries. It's not like working with native integers, but the possibility is there. Then you can do precondition testing, but there are challenges. Just think about this. Like if I would tell you like, okay, you have to add A and B together, but first you have to check whether it will overflow. How you would check that? If you would check it like this, that's not good. This is in red background and in red frame. That's a convention on our slides. So whenever we have a bad code, it's in red background, and whenever we had good code, it's in blue background. So why this is not good? Because obviously if the overflow would happen here, the overflow will happen here as well. So basically this is exactly the definition of int max. No value can be bigger than int max ever, right? So there is no way something can, so this is an always true condition. Basically, it doesn't make any sense to check it like this. You can do it actually, and it's even more complicated than this, but just to give you some insights into how you have to think. Once again, it's not the obvious way of how you can write this down, but you can basically do something like you put this b on the other side of the inequality and say you don't check whether a plus b would be smaller than int max, but you check whether a is smaller than or smaller or equal than int max minus b. But in this, you also have to take into account b being negative. So basically, with a bit of complication, you can pretty much easily arrive to something which is mathematically equivalent to saying a plus b smaller or equal than int max. But this is not something that can overflow because we all the time go off the critical section, and that is the correct way of writing precondition testing. Post-condition testing is much more trivial. So you basically do the arithmetic operation and just take a look at the results. So if for a positive b, a plus b is not bigger than a, then we detect that we cross the red line. It's so simple. If b is negative, then a plus b should be smaller than a. If it is not, we cross the red line. So basically, this is something we can easily detect. So in this case, we do the arithmetics and check it afterwards, check the result afterwards. And specifically for C++, you also have some nice libraries like, and also for C, but let me talk more about C++. So you have the safe numerics from Boost or SafeInt, which are all template-based C++ libraries. You can template your integers. And the most important feature of these is that when you cross the red line, it will be an exception. There will be an exception. And of course, as a consequence of this, now that means that all of your arithmetic operations you have to put into try block and catch the exception upon, crossing the red line. But at least to say you have a chance to get notified or be notified about the fact and then do something about it. But just imagine the last a plus b in your code now should be put in a try block. It's not easy to switch your mind into this way of thinking, but this is what you need to do if you want to handle as much as possible correctly all the integer problems in your code. So with this and with some overtime, I'm finishing with a single slide, which is basically something you already have seen and I already mentioned. So how do we teach integer problems as well as many other problems related to reflection, related to buffer overflow in C, C++, related to input validation, approaches to input validation, cryptography, authentication, authorization, and so on and so on. We show the problem. So this is step number one. We always show people the problem, as you have just seen here, the ring and the overflow, but we don't stop there. We show them hacking techniques. We show developers hacking techniques not to turn them to the dark side, not to make them hackers, but to frighten them, because we need emotional engagement of developers. They need to understand that this is a problem. We cannot just say, okay, I'm in rush now, I have a deadline, so I will deal with security later on. There is no way. There is no way you will do this. You have to wave in the ways of how you think about your code from security point of view. So we show hacking techniques so that they are aware of the consequences, and then we focus, of course, on the best practices. So we discuss in much more details this precondition testing, post-condition testing, big num libraries, template-based C++ libraries, and so on and so on. Then we fix the code in most cases. I will not show you like how we fix the code, the code that you have seen here, but we then have a next lab integer handling best practices where we fix the source code, and we see that the problem that we have seen before does not work anymore, or the hacking technique does not work anymore. And then, of course, present real-life case studies, like I just rushed through very, very quickly through the WannaCry story. Unfortunately, there are millions of such stories. So in this, Cydrill Sergeant helps us a lot. You have seen a quick demonstration about what this Cydrill Sergeant is all about. So it is a chatbot, and where you can find all these courses. You can find the courses on Informator's website. You can see here the URL, but you can just Google for Informator, or you can just visit the Informator website and you will find their secure coding courses in C++, but also not only there, but also Java, C#, Python, so many other programming languages, platforms, and so on are also covered. But you have to know that also there are certain vertical courses like banking and finance, automotive, healthcare, machine learning. What makes a course a vertical course is that it's still, of course, it's still a C++ course, but we talk a little bit about the extra threats in that domain. We bring the case studies from that domain, and we also just present quickly the standards and the whole like environment from automotive or from healthcare, if you happen to be a company which develops software in that line of business. So with this, I would like to thank you for your attention.